Dear listeners, thank you for your interest in this new episode. I am Jeff's voice avatar. In the previous show of From Know-How to Wow, your hosts Melina and Shuko made it quite clear that lasers are the coolest technology on the planet. They are becoming even cooler with new beam shaping capabilities. In this episode, Bosch researcher Peter Stritt will share more details on how beam shaping works and what it can do.
From know-how to wow.
AI hosted Deep Dive.
Beam shaping technology is becoming increasingly important in laser material processing. It makes lasers more flexible and adaptable. This is enabled by optical elements that deflect parts of the laser beam. There is even more to it, says Bosch researcher Peter Stritt.
The so-called coherent beam combining, where we have different laser beams being combined. Due to their coherency, they can be actually combined to form, again, one single beam shape, and that beam shape can be changed and formed very dynamic.
Most people have probably seen a laser show somewhere. Lasers paint different shapes just by moving the dot-shaped beam really fast. Faster than the eye can follow. So people can't see the dot moving. They just see the resulting shape. Beam forming is very similar to that.
We are actually doing the same thing. However, we are in another time scale. What you are talking about is the visibility for the eye, which is more in the 50 Hertz up to 100 Hertz region. So if we have a fast movement of the laser beam for a laser show above 100 Hertz, then we would just recognize the shape. And now what we do in laser material processing, in order to get a good process and in order to get a steady shape, we need higher frequencies. So what we use in laser material processing is more in the kilohertz or even up to nanoseconds range, so megahertz range.
Let's assume that the beam moves in a triangular shape. At 100 Hertz, you could say that it is still a round beam forming a triangular angle. In the megahertz range, you could argue that the beam itself has a triangular shape.
When is a beam defined by movement and when is a beam considered to be static? And that actually depends on the time scale.
In terms of resultant heat conduction effects, at a certain speed, the dot moving along the edges of a triangle becomes indistinguishable from a static triangle.
From now, it is just possible to form such a triangle, and it is our task in the research to find out whether this triangle is beneficial somehow.
That's multiple questions Peter and his co-workers have to answer. One of these questions is, what are interesting use cases for beam shaping lasers? Another one can be, how to best tackle these use cases with beam shaping lasers. And regarding the first question, Peter has got some ideas.
On the one hand side, you have a certain material and want to join it to another material, so you don't have symmetry in the molten zone. Or on the one hand side, you have a structure which is very thin and you want to join it to a larger structure. And to melt both parts, then you would need less energy on the thin material side than on the thick material side. And to get that portion of energy into the different material shapes, you need to somehow shape the beam or at least shape the power of your laser beams.
Another issue can be addressed by these new lasers. The spatters. Molten material is ejected out of the weld pool. That's often a problem with the classic Gaussian beam shape.
There is evaporation and you have the formation of a so-called capillary, welding capillary. And in that, the evaporation then can introduce spatters.
Peter and his colleagues found out that a laser beam with an additional outer ring can help reduce those spatters. He discussed this in the previous episode. The ring stabilizes the capillary in the molten material. Peter also calls the capillary a keyhole. The ability to control the keyhole could prove even more useful.
By moving that keyhole through the molten material, you can actually stir inside the melt pool.
You can stir molten metal with light. Let that sink in. It's like a spoon moving through a hot soup.
You actually have a better effect if you not only use one capillary or one spoon to mix your materials. It is even beneficial to use more than one spoons or several capillaries, and that is done by laser beam shaping.
Doing this, of course, serves a purpose. Being able to stir a melt pool can have several advantages.
This is increasingly interesting if you want to influence the melt flow during the laser welding process of different materials. Because by the movement of the laser beam, you can increase the mixture of the two materials and thereby define some certain material properties like the strength or the heat or electrical conductivity.
The difficulty is to figure out which beam shape works best. The options are almost infinite. So, Peter Stritt conducts a lot of experiments. And he collaborates with an AI that ingests the experimental results to then suggest the parameters for the next experiment.
We have different sensor systems which are partly used in the process and partly post-process to measure the quality of the laser process itself. For example, in process we use camera systems, or we use extremely fast photodiodes to observe the emitted light of the process itself. And then the second thing I mentioned was the post-process sensors. And here we can do X-ray analysis of the weld and thereby identify defects. Or we even do destructive testing with the performance tests of pull tests, and we do metallurgical cross-sections to observe inner material defects. And from all the collected data, we can actually derive the quality of the weld and have a good measure here for the quality.
Peter and the other experts at Bosch Research feed this data into the AI. Also, their expert knowledge trains the AI. They do this by marking areas of interest on the weld images or by labeling indicators of an issue they see. Additional to this, a third data source comes from across Bosch. This source also helps teaching the AI about quality measures for laser processes.
At Bosch, we are in the beneficial position that we have production processes with a large number of production units, and thereby we gain a lot of data. And thus this enables us to have a good feedback loop to the AI system and to collect good data.
Peter collects both know-how and latest findings. He can then transfer this into innovations and new production processes. The result is new and better products for the customers simply by shaping a beam of light. I hope you learned something. And you know what? Our December episodes will be about AI-enabled process automation as well. It is going to be delicious. That AI helps people achieve perfect results in their kitchens. Stay curious.